Okay, let's go ahead and get started. So today what I want to do is continue our discussion of gauge theories. And that is in particular the simplest gauge theory, known as U1 gauge theory, i.e. electromagnetism. Okay. So as we reviewed last time, when we talk about electromagnetism, it's very useful to do so in a formalism where Lorentz invariance is manifest. So rather than working in terms of the electric field and magnetic field, we'll work in terms of the electromagnetic field strength, F mu nu. So F0I is equal to the EI, the ith component of the electric field, and the Fij's are equal to the various components of the B field. And F is an antisymmetric tensor with 6 degrees of freedom. The 4x4 antisymmetric matrix has 6 degrees of freedom. And so this is just a different packaging of the 6 degrees of freedom that are in the 3 components of the electric and magnetic field vectors. Now, when we talk about electromagnetism and gauge theories in quantum field theory, instead of working directly with the electric and magnetic fields or the electromagnetic field strength, it's somewhat more convenient to work with the potential, which is the 4-vector A mu, that is the Lorentz invariant generalization of the electric potential or vector potential of electromagnetism. This is called A mu. Its 0th component is the electric potential. Its I components are the vector potential. And its derivatives give you the electric and magnetic fields through this formula that I've written right here. Okay. The equations of motion of electromagnetism are Maxwell's equations, which can be written in covariant form essentially as the derivative of F mu nu, where you contract the 2 of those indices together, is equal to the current 4-vector. Okay? Or in vacuum, that is to say, with no external sources, just d mu, F mu nu is equal to 0. Okay. So that's one of Maxwell's equations, and the other Maxwell equation follows directly from the definition of F as a derivative of A, and that's the statement that the derivative of F plus various cyclic permutations is equal to 0. Okay. So this is sometimes not regarded really as an equation of motion, but rather just as a mathematical identity, which follows from the fact that F is defined in terms of the derivative of A in this way. Okay. So the second equation is sometimes referred to as the Bianchi identity. And it's not really an equation of motion as such. It's just a consequence of the fact that F is this partial derivative of A. Okay. And Maxwell's equation follows from an action, as you verified on either your first or your second problem set, I don't remember which, so that the action of electromagnetism is just the square of F mu nu with an additional term that reflects the coupling of A to a current J. Are there any questions on this so far? So hopefully this is all reasonably clear. By the way, just for my information, when you took your electromagnetism courses, did you see the field strength tensor A mu? Is that something that you saw, more or less? Okay, so this is all fairly familiar to you. Good. And the final thing that we should point out is that the equations of motion are invariant under gauge transformations. In particular, if you take a mu and you shift it by the derivative of any function lambda, then F mu nu will be invariant. And in particular, Maxwell's equations, the equations of motion, will be unchanged. Yes, there's a question. Sorry, what was that? Oh, I'm sorry. Yeah. Yeah, I always, yes, thank you. Yeah, I'm always mixing up what I call Lagrangian and what I call action. It's hopefully clear from context. If it's got an integral, it's an action. If it doesn't have an integral, it's a Lagrangian. Good, thank you. Any other questions, comments? Good. And it'll turn out, as we'll see today, that this principle of gauge invariance is really absolutely crucial, both in understanding classical and especially quantum mechanical electrodynamics. Okay? And so indeed, it's this basic principle of gauge invariance that's we're going to spend some time investigating when we talk about electromagnetism, because it's this principle that's going to be generalized when we talk about the fields of the standard model of particle physics. So all of the force carriers of nature, not just the photons which transmit the electromagnetic force, but all of the other particles that transmit the nuclear forces and indeed the gravitational force, can be viewed by thinking about them in terms of this gauge invariance. Okay? So that's a principle that we'll really return to again and again in this class. Okay. So what I'd like to now do is just try and think about the quantization of this theory. So I'd like to proceed along very similar lines as we did when we quantized a free scalar field earlier on in the semester. Okay. So let's just begin by writing down the equations of motion a little bit more clearly. Okay. So the equations of motion, d mu, F mu nu equals 0, can be written not as equations for F, but as an equation for the four potential A. So using the fact that F mu nu is a derivative of A, you could just go ahead and plug that into Maxwell's equations, and you get a second order differential equation for A. So what is it? It's d mu A nu, just coming from that first term here, and then you have to subtract off the second term, which we could write as d mu A mu. Okay. So that's the equation of motion that A obeys. And the first thing that you should notice is that this looks very similar to the equation of motion of a free scalar field. That is to say, this first term here looks very similar to the Klein-Gordon equation for a massless scalar field. Okay. The second equation, however, looks slightly different. So what we need to understand is to what extent we need to worry about that second term when we try and think about the quantization of the theory. Okay, so given this equation of motion, you might think that you could just proceed in a completely straightforward way by expanding A in a basis of solutions to the equations of motion, promoting the coefficients in that expansion into operators, which would be raising and lowering operators that would create and destroy particles, just as you did in the scalar field case. And that's indeed more or less how it works, except that there are a few subtleties that arise, which I think we'll need to spend at least a few minutes discussing. Okay. So let's imagine trying to quantize the theory. Okay. So if you were to write the Lagrangian in terms of A rather than F, well, it's just the derivative, it's just F squared. F is the derivative of A, anti-symmetrized. So in terms of A, you'll get an expression for the Lagrangian which looks something like that. All I've done here is I've used this expression here. I've inserted the definition of A into F, and I've combined some terms which turns that 1/4 into a 1/2 there. Okay. But the first thing that you'll notice if you look at this is that this Lagrangian doesn't contain the time derivative of A0. Okay. So we want to think of A0, A1, A2, A3 all as independent fields. But the first thing that we did when we were quantizing a field is we had to write down the momentum conjugate to that field. Okay. For example, when we quantized a scalar field, the momentum conjugate to phi was the derivative of the Lagrangian with respect to phi dot. Okay. And then you wrote down, for example, canonical commutation relations between phi and pi, which led to the commutation relations of the harmonic oscillator algebra that we used to construct the Hilbert space of the theory. In the present case, we're finding that, in fact, A0 does not appear to have a canonically conjugate momentum. Okay. So there doesn't appear to be a momentum conjugate to A0. Sorry, what's what? Yes. Oh, I'm sorry. I just forgot an A here. Thank you. Yes. Yeah. So you're supposed to raise your hand and interrupt me when I make mistakes like that. Thank you. Good. Any other questions? Yes. Okay. So this makes it look like the Lagrangian is a function of A0, but not its time derivative. Okay. So you might wonder then that there's somehow no dynamics for A0. And indeed, this would lead you to ask the question is, can we just set A0 equal to 0? So the Lagrangian is independent of the time derivative of A0. So you might think that you could just set A0 to 0 somehow. And indeed, the answer is yes. Okay. And in particular, one has to use gauge invariance. So how does that work? Well, the basic idea is that gauge symmetry, that is to say, the symmetry of the equations of motion under the shift of A by a total derivative, can be used to simplify the equations of motion, and in particular to remove degrees of freedom from the theory. So whereas naively you might think that A mu is a theory with 4 degrees of freedom, that electromagnetism should be described by 4 functions, that each of which depends on space and time, what we're going to see is that because we have this gauge symmetry, there are in fact only 2 degrees of freedom, and these degrees of freedom correspond to the physical polarizations of a photon. And it's this imposition, it's this use of gauge symmetry that's really going to be very useful and important when we try and quantize the theory. So the basic idea is the following. So what we would like to do is we would like to impose some additional constraints on A mu such that for each A mu satisfying these constraints, there is a unique F mu nu. Remember, the point is that if you shift A mu to A mu plus d mu lambda, F mu nu is unchanged. Okay? That means that there's some redundancy in our description of electromagnetism. Each A mu, many different A mu's could lead to the same F mu nu. So what we'd like to do is understand whether it's possible to impose some constraints on A mu such that for any A mu that solves these constraints, you can find a unique F mu nu. Okay? And this procedure is known as gauge fixing. In particular, what we're doing is we want to remove all of the ambiguity in A mu that arises because of this gauge symmetry. So let me give you a very simple example. And this is not actually the sort of gauge fixing that we'll be doing typically in this course, but it's the simplest example of gauge fixing that one can understand. So let's imagine that we have some vector. Okay. So, for example, this vector could be 0, 1, 0, 0, 0. Okay, it could point in the x direction. Okay. So this would be the vector x hat, if you know what I mean. Then you could imagine the component of A in the x direction, that is to say, n mu contracted with A mu. And you could ask how this changes under a gauge transformation. Well, under a gauge transformation, it will pick up a piece that looks like n mu d mu of lambda. Okay? Or n mu a mu will pick up a piece that's just, in the case where n mu points in the x direction, d by dx of lambda. So you could then imagine doing the following. You could say, given some particular value of A mu, we could always choose lambda such that d by dx of lambda is equal to n mu A mu. Or I guess I should put a minus sign there, so that after you do a gauge transformation, n mu A mu will be set to 0. And then the only question that you have to ask is whether you can always solve this differential equation here. So given some value of A mu, this is a first-order differential equation for lambda. And it's easy enough to solve simply by saying that lambda will be the integral of n mu A mu. So given some value of A mu, you just integrate it dx to solve the equation that sets n mu A mu equals to 0. Okay. So what does this mean? This means that indeed you could always do a gauge transformation that would set A0 equals to 0. You would just choose n mu to be the vector 1, 0, 0, 0, 0. Now, in fact, the gauge fixing procedure we'll use in this course is going to be a little bit more sophisticated, because it turns out that the gauge fixing procedure where you just set A0 equals to 0 directly has some unpleasant features when you try and quantize the theory. But nevertheless, people do sometimes try and study gauge theory using this particular gauge fixing procedure. So just to for the purposes of your education, so if n mu points in a time-like direction, so for example, if n mu is 1, 0, 0, 0, 0, then this is known as temporal gauge. If n squared is equal to 0, that is to say if n points in a light-like direction, then this is known as null gauge, or light cone gauge. And if n squared is less than 0, so that this is some sort of space-like vector, then this is known as axial gauge. Okay. So these are three different examples of ways that you could impose some condition on A, which would restrict then the possible allowed potentials that would appear when you, for example, try and find solutions to the equations of motion. What I would like to do in this class is something a little different. So in particular, I'd like to consider the following. So remember, our initial problem was that there was no time derivative of a0 that appeared in the action. And so the question then is whether you could consistently set a0 equal to 0. So the reason why that might be difficult is that if you look at the equation of motion for a0, okay, so let's just look at this equation of motion up here for a. So here's the equation of motion for a. If you look at the equation of motion for a0, what does it say? Well, so the equation of motion for a0 is that d mu of a0 minus the time derivative of d mu a mu is equal to 0. Or if you expand that out, that's the statement that minus the Laplacian of a0, so this here is the spatial Laplacian, dj dj, where j runs from 1 up to 3, plus d by dt of del dot a, where a is the usual vector potential, a1, a2, a3, is equal to 0. Okay. So the time derivative here, the a0 double dot term has canceled the a0 double dot term coming from here, and you're just left with an equation which says that the spatial Laplacian of a0 is the time derivative of del dot a. Okay. So the fact that there were no time derivatives of a0 in the equation in the Lagrangian is reflected here in the fact that there are no time derivatives of a0 in this equation of motion. So the question then is, can we consistently set a0 equal to 0? And you can see that in this equation of motion that this will be possible only if del dot a is equal to 0. So we'll need to set this term equal to 0. So is that possible? Well, the answer is yes. Okay. So in particular, what we will do is we'll use what's known as Coulomb gauge, where we set del dot A equal to 0 by some judicious choice of that gauge parameter lambda. So in particular, just to convince yourself that you can always do that, under a gauge transformation, del dot A will go to del dot A. So remember, A goes to A plus the derivative of lambda. So the spatial part of A goes to A plus the gradient of lambda. So del dot A goes to del dot A plus the Laplacian of lambda. So that means that if you want to set del dot A equals to 0, what you need to do is you just need to solve Laplace's equation, that del squared of lambda is equal to minus del dot A. Okay. So we can set this to 0 by choosing lambda such that grad squared of lambda is minus del dot A. Okay. Yes.
We chose the Lorentz gauge for the vector A.
Yes.
Wouldn't the equations of motion for A just reduce the time derivative?
Yes, so that's absolutely another gauge choice that one could make. And indeed, we will be using that gauge choice later on in this course when we study the quantum theory. Okay.
So then why is this one different?
Well, why is it nice? I mean, let's put it this way. A choice of which one is nicer or less nice is sort of, it's a spiritual choice. So different gauge choices are useful for different reasons. So, for example, in Coulomb gauge, in Coulomb gauge, in Coulomb gauge, when we work out the solutions to the equations of motion, they'll look especially nice. And in particular, they will be exactly the sorts of plane wave solutions to the equations of motion that you're familiar with from your classes in electromagnetism. One could also, of course, work it out in Lorentz gauge or in any one of a number of other gauges, and you would get the same thing physics-wise. I mean, the point of a symmetry is that physics is invariant under that symmetry. I'm going to use Coulomb gauge today because I think it makes all the things you're familiar with in terms of like polarizations of the photon and so forth a little bit more familiar. But when we actually work out the Feynman rules for electrodynamics and so forth, we're actually mostly not going to be using Coulomb gauge. We'll be using other sorts of gauge choices. Okay. So yeah, I mean, to some extent, your gauge choice is often aesthetic. Different gauge choices may be useful in different situations. Okay. Just as whenever you use a symmetry, whenever you have a symmetry, you always, your strategy is always to look at the problem at hand and then try and make a choice of symmetry, to set things up using the symmetry to make your equations as simple as possible. Okay. So today I'm going to use Coulomb gauge because it's going to make some of my equations quite simple. Next class I'll be using Lorentz gauge or Feynman gauge. Okay. Good question. Other questions? Okay. Good. Okay. So what we've done is we've chosen Coulomb gauge so that del dot A is equal to 0, but we still have some residual gauge symmetry. Okay. So remember that under a gauge transformation, A0 will go to A0 plus lambda dot, the time derivative of lambda, and A0 will solve the equation of motion in Coulomb gauge. So there's the equation of motion in Coulomb gauge, which reduces to just the statement that grad squared A0 is equal to 0. So what that means is that because grad squared of A0 is equal to 0, we could always choose lambda to be the integral dt of A0, and that will obey grad squared lambda is equal to 0. And in particular, it will preserve this Coulomb gauge condition. So in particular, if you set lambda equal to the integral dt of A0, then, or I guess with a minus sign here, then because A0 solves the Laplace's equation, that will leave del dot A unchanged, so that you can simultaneously set A0 equal to 0 and impose the gauge condition that del dot A is equal to 0. This is a sort of common trick where, what we're doing here is sort of remarkable because lambda contains 1 degree of freedom and A contains 4 degrees of freedom. So you might think that you could use gauge invariance to remove one of those degrees of freedom from A and get 3 degrees of freedom left. But what we're actually seeing is that you can simultaneously impose two constraints on A. So we're really removing 2 degrees of freedom from A using one gauge condition. And it follows because we can do this because we're using the gauge condition and the equations of motion. So the counting of degrees of freedom that one does in electromagnetism is the following. You start with 4 degrees of freedom from A mu. You lose 1 by imposing gauge symmetry, and another from the equations of motion, and you're left with a total of 2 degrees of freedom. In particular, A0 has been set equal to 0, so the remaining equation of motion so let's just look at the equations of motion here. So this was the A equation of motion. We can now set nu equals to AI, and this guy here is just d by dt of A0, which is 0, plus del dot A, which is 0. So the remaining equation of motion is just d mu A mu of A is equal to 0. And this is just like a massless scalar. Okay, so that means that it's almost trivial to write down the solutions to the equations of motion of the theory. In particular, a general solution to the equation of motion is going to be a plane wave. So it'll take the form of the integral d3p of e to the I px, where px is just shorthand for p mu x mu, the 4-vector p contracted with the 4-vector x, where p is determined by the condition that A is massless, so p squared is equal to 0. So p0 would be plus or minus the square root of p vector squared. And then there needs to be some prefactor, so A is a vector, so the solution needs to be a vector, that I'll call epsilon. And epsilon can be some vector that depends on p. And the only constraint is that del dot A is equal to 0, which implies that if you just take the derivative of del dot A of this equation here, then the derivative will bring down a factor of p from this exponential here. So this will be a solution of the equations of motion consistent with the gauge condition that del dot A is equal to 0 if p dot epsilon is equal to 0. Okay. So at this being the gauge condition in Coulomb gauge, that del dot A is equal to 0. And so what this means is that you're left with 2 degrees of freedom. That is to say, 2 polarizations for this vector epsilon. Okay. So, for example, just to make this completely explicit, if we want to consider an electromagnetic wave moving in the z direction, so that p is proportional to z hat, then there would be 2 possible solutions for epsilon. You could take epsilon to be, say, proportional to x hat or proportional to y hat. And the two solutions would describe a electromagnetic wave that's linearly polarized either in the x direction or in the y direction. So what we see here is that by going to Coulomb gauge, we have the polarizations of an electromagnetic wave are transverse to the direction of propagation of the wave. This presumably is something you more or less saw in a class on electromagnetic waves. Often, sometimes, it's more convenient. Yes, question.
On the count of user freedom, maybe I'm missing something. The minus one in the case counts for if delta equals 0 or k0 equals 0.
Well, okay. I mean, which one you want to call gauge and which one you want to call equation of motion is a little bit ambiguous. Okay. Yeah, okay. You could call them both gauge, but with help from the equation of motion. Okay, if you like. I mean, whether you call one of them gauge or one of them equations of motion, or two from gauge and equation of motion, is a little ambiguous. The point is that the number of gauge effective degrees of freedom you can remove because of the gauge symmetry gets doubled because of the equations of motion. Okay. And the reason why I introduced the counting this way is that this is exactly how the counting works in other more interesting gauge theories. Okay. So, for example, just for your education, let's imagine we were considering gravity instead of electromagnetism. So in gravitational theories, you have a metric tensor, G mu nu, which is a symmetric 4x4 matrix, which has 10 degrees of freedom. The analog of the gauge symmetries are the coordinate transformations. Okay, so you have 4 functions, x mu, that can be written in terms of 4 other functions. You can do, so there are 4 degrees of freedom. So you subtract 4 here from coordinate changes, and then that gets doubled by that same procedure where you can actually remove 8 degrees of freedom instead of 4 by imposing the equations of motion, and you're left again with 2 degrees of freedom. Okay. And what are those? Those are the 2 possible polarizations of a gravity wave. So, this sort of counting where you remove 2 degrees of freedom for each gauge symmetry is useful. Okay. It, for example, allows you to immediately see why there are only 2 possible polarizations for a graviton, or for a gravity wave, without actually doing any work. Good. Other questions? Okay, so frequently we like to use these linearly polarized solutions of Maxwell's equations, but sometimes it's useful also to use circular polarization. In that case, you would introduce 2 different polarization vectors that we would call, say, epsilon plus and epsilon minus. So, which would be complex polarizations. X plus IY and X minus IY. Okay. And then, as usual, of course, A is a real field at the end of the day. So when we introduce a complex polarization like that, to get a real solution of the equations of motion, we just take the real part of A at the end of the day. But you get something non-trivial because the i's appearing in epsilon here will mix with the i's that appear in the e to the ipx here, and you'll get some more complicated looking solution to the equations of motion. But the point is that we now have a complete basis of the solutions to the equations of motion. So each epsilon times e to the ipx is a solution of Maxwell's equations, just like the plane waves of a scalar field. And so we can go ahead and quantize electromagnetism just as we did for a scalar field. In particular, what we do is we imagine writing a general solution of electromagnetism as expanded in this basis. So we just choose our favorite basis of polarization vectors. There'll be two of them because there are two polarizations for an electromagnetic wave. So I'll call them epsilon 1 and epsilon 2 and label them by an index I. And then we expand in terms of these solutions to the equations of motion with some coefficients that I'll call A sub pi and A sub pi dagger. So if I didn't have those epsilons there, then this would be precisely the equation that we're already familiar with, where you take the scalar field and you expand in terms of a basis of plane wave solutions to the Klein-Gordon equation. Here, all I'm doing is including the fact that the plane waves, there are two different types of plane wave solutions to Maxwell's equations, which correspond to the two polarizations of the vector field A. And so we now get two different types of expansion coefficients, what I called AP1 and AP2, corresponding to the two different types of polarizations. And the idea, when you quantize the theory, is that you take these coefficients that appear in the Fourier decomposition of A, and you promote them to operators. Okay? And in particular, these two operators have to be Hermitian conjugates of one another. AP dagger is the Hermitian conjugate of AP. In order for this operator A to be a Hermitian operator, okay? That's also why I took this complex conjugation here, to make sure that A is a Hermitian operator. And these operators, API and API dagger, will obey the usual canonical commutation relations. So these will be Fock space operators, which obey the usual canonical commutation relations. So let's, in particular, their commutator will be 0 unless I is equal to j and P1 is equal to P2. And I've introduced a normalization factor here, as I usually do, just to make my life simpler a little bit later on. Okay. So this means that we've quantized electromagnetism, just as we did for the harmonic oscillator. So, or just as we did for the scalar field. So the Hilbert space of electromagnetism is just the product of an infinite number of harmonic oscillators. There's a vacuum state, which describes a state with no particles in it. There are now two different types of one particle state. Corresponding to the states with one photon, with either choice of polarization labeled by that index I. And so you can hopefully see that the construction here mirrors very closely our construction for a scalar field. All that happened was that we now have a more complicated set of raising and lowering operators to keep track of the fact that the particles that we're creating now have spin. That is to say that they have polarizations. Okay. And so that there are two different kinds of photons corresponding to the two different polarizations. And when we write down our Feynman rules that describe the interactions of photons with other sorts of matter, we'll have to keep track of the fact that there are two different polarizations of photons. And so there's going to be a little extra data that appears in our Feynman diagram which forces us to keep track of these polarizations. But otherwise, the procedure is going to be more or less the same as it was for a scalar field. Question? That's correct. Another way of saying that is there are two possible helicities for the photon. There's two possible polarizations for the photon. So, yes. So spin 1 refers to the number of, yeah. Okay. So in quantum mechanics, you learned that a general spin 0 system has 1 degree of freedom, spin 1/2 has 2 degrees of freedom, spin 1 has 3 degrees of freedom. If you write, a photon and electromagnetism describes a special type of spin 1 system, one with gauge symmetry that really removes one of these degrees of freedom. A more general spin 1 theory, okay, which is something that actually is not something that we'll talk about now, but which will be very important later on in this course. A more general spin 1 theory would be a theory of a so-called massive vector, which is one where the Lagrangian would take the form we wrote down earlier, but with an additional term. So if you think about it, the only other term you could write down that is a scalar that's quadratic in the a's would take the form of m squared a squared. And this term gives a mass term to these vector fields. And if you went ahead and studied this theory, you would see that it does not have any gauge symmetry. Okay? It's not invariant under a mu goes to a mu plus the total derivative. And so because of that, you'll have 3 degrees of freedom rather than 2 degrees of freedom. So roughly speaking, if you wanted to describe this theory, if you think about a photon propagating in the z direction, then a usual photon has 2 transverse polarizations in the x and the y direction, but it has no longitudinal polarization in the z direction. A massive vector theory would have a polarization in the z direction. And in fact, massive vector theories appear all over the place in physics. The nuclear forces are described by vector fields that have an effective mass, unlike the photon. In superconductivity, the electromagnetic field acquires a mass. Okay? That's essentially why superconductors are superconductors, is because the effective electromagnetic field, the effective Maxwell field A inside a superconductor is massive rather than massless. Okay? Any other questions? Yes.
You choose a specific norm for the group.
Mm-hmm. That's right. I mean, I chose a norm, yes. So I chose the norm so that epsilon squared is equal to 1. And that's because at the end of the day, I want this canonical commutation relation for the a's to be appropriately normalized. Good. Thank you. Yes?
Wasn't you have a massive scalar where n squared is very, very small?
Yes.
Can you treat it as an almost gauge symmetric vector field where you introduce the longitudinal polarization?
Okay. Yes. So, so you mean an almost massless a vector field? Yes, absolutely. I mean, you could imagine weakly broken. So you can always, I mean, in general, whenever you have a symmetry, it's very useful to think of cases where that symmetry is weakly broken. Okay? So, for example, a proton and a neutron are very nearly have the same mass, but not exactly. So you could think about an approximation scheme where they have exactly the same mass, and then you could think about the rotations between the proton and the neutron. This is called isospin. And then you could think about the theory of the world where they have exactly the same mass, and then you could work, and then that would be a pretty good approximation to nature. Okay? And so it's always a good idea to do that. And so there are indeed, and we will see indeed probably in this course, cases where you can think about, say, weakly broken gauge symmetries. So, for example, there are going to be cases where we have gauge symmetry theories which have classical symmetries that are broken quantum mechanically. Okay? That's a classic sort of case where quantum mechanics leads to the breaking of symmetries, and h bar is small, so they'll be small. Good.
There is an I factor here also?
Probably.
I don't know.
Yeah.
The A is
No, there's no. So the typical normalization is that x and p have an I, so phi and pi have an I, the field in their canonical commutation, but A and A dagger do not. Yes. Good questions? Okay. So this means that if you want to quantize a box of radiation, then you know how to do it. You know exactly what the quantum states are of a box of radiation. And these are the quantum states that Planck was studying when he came up with his resolution of the ultraviolet catastrophe for black body radiation. Okay. But boxes of radiation are sort of boring. What we really want to study are the interactions of electromagnetism with charged particles. Okay. So what I'd like to do now is ask, how can we couple electromagnetism to charged particles? And the basic principle that I'm going to use is that I'm going to start trying to write down the equations of motion, or the action describing electromagnetism, coupled to some charged particle. But I'm going to demand that we preserve gauge invariance. In particular, we saw that in the case of electromagnetism not coupled to anything, gauge invariance was crucial in deriving the fact that there are only two polarizations of the photon. And if you don't want more polarizations of the photon to appear, then you have to preserve gauge symmetry whenever you couple electromagnetism to some other sort of matter. So the question then is, how should we describe a charged particle in quantum field theory? So the first thing that we know is that if you have some sort of charged particle, then you have a field associated with it. And from that field, one should have a conserved current, which is the thing that will appear as a source term in Maxwell's equations. So the only sorts of fields that we can couple to electromagnetism are those that have conserved currents. So, for example, if you take a real scalar field, say, which obeys Klein-Gordon equation, then there are no conserved currents that we can construct from phi. The simplest theory from which we can construct a conserved current is not a real scalar field, but a complex scalar field. As you saw in one of the earliest problem sets in this course, a complex scalar field is just a fancy name for two real scalar fields. But rather than writing down separately the action and equations of motion of a complex of two real scalar fields, we can write down the action and equations of motion of a single complex scalar field. So for example, if you have a complex scalar field phi, so phi is a complex number for each point in space-time, then the action will take the form of d mu phi bar minus m squared phi bar phi. Okay. And one of the things that I think you verified on an earlier problem set is that if you divided phi into its real and imaginary part, so that phi is phi 1 plus I phi 2, then that this Lagrangian would precisely be the sum of the Lagrangians for two real scalar fields, phi 1 and phi 2. Did you do that on one of your problem sets? I gave that to you? Okay. So a complex scalar field is just a fancy way of writing down two real scalar fields. But they're two real scalar fields which have the same mass. And because of that, there's a symmetry where you can rotate these two scalar fields into one another. Just like if the proton and the neutron have the same mass, and you forget about the fact that the proton has charge, you could think about the rotation, the symmetry that rotates the proton and the neutron into one another. So in particular, the symmetry of a complex scalar field is the one where phi goes to e to the I lambda times phi, where lambda is just now some number, and phi bar goes to e to the minus I lambda times phi bar, so you can immediately see that this Lagrangian is unchanged under this rotation of phi to e to the I lambda phi. And then it's straightforward to go ahead and write down the current using Noether's theorem associated with this symmetry. This is something that, did we do this in class, or did you do it on your problem set? You did it on your problem set. So the answer is I times phi d mu phi bar minus phi bar d mu phi. Okay. So remember, Noether's theorem says that a conserved current is the derivative of the Lagrangian with respect to phi dot times delta phi, where delta phi is the variation of the field under the symmetry. Under the rotation, phi goes to e to the I lambda phi. Phi rotates into phi bar, and phi bar rotates into minus phi, which leads you to this current that you have right here. Okay. And Noether's theorem only determines the current up to an overall constant. It just constructs for you some conserved quantity. And we put an I out front so that this current is real, because the quantity in the parentheses that I've written here is something minus its complex conjugate. So you have to multiply by an I to get something real. Okay. And then there's a minus sign just because, I don't know if that's how it's written in the book. Okay. So we have this conserved current here. And so naively, you might try and describe electromagnetism plus a charged particle by the following Lagrangian. You would just write down the action of electromagnetism plus the Lagrangian of this charged particle, and then you would couple them using the term that we wrote down in our derivation of Maxwell's equations. A mu, J mu, where J mu is just the current of the complex scalar field. Okay. Yes?
How do you know that this current carries a charge? Because it can
Okay.
be a probability current, for example.
Okay. So remember, okay.
Or no, or another kind of...
Let's put it this way. A complex scalar field is one that has a conserved current. if I want to interpret that conserved current as an electromagnetic current, then it has to couple to electromagnetism. That's what it means. Okay. So you could imagine, it's not the case, so it's certainly not the case that every complex scalar field couples to electromagnetism, but rather that the coupling of the current to electromagnetism is what I mean by that particle having charge. Okay. Is that sort of clear what I mean? Okay. Let me give you maybe another example. I could imagine that I have two complex scalar fields, and I want them to describe particles that have different charge. Okay. Then how would I do that? Well, what I would do is I would write down A mu J mu for the first one, and then A mu J mu times 12 for the second one, if I want the second particle to have 12 times as much charge as the first particle. Okay. However, what I've written down here for the Lagrangian is wrong. Okay. Can anyone tell me why it's wrong? It's late in the day on a Thursday. So how many of your brains are working? Yes. Okay. That's right. Okay. It's not gauge invariant. That's one reason why it's wrong. The reason why I was actually thinking that it's wrong is that it's also, J mu is actually no longer conserved once you write down this term. The reason being that Noether's theorem, we now have a coupling between phi and d mu phi, and a mu, so that the additional terms coming to the current coming from that coupling. Okay. So what that means is that there are going to have to be additional terms that appear here that you need to include in order to make this current conserved again. And indeed, as was just mentioned, this thing is also not gauge invariant. Okay. Although it's almost gauge invariant. In particular, remember that if you have a Lagrangian that looks like this, then under a gauge transformation, F is invariant, and A picks up d mu lambda j mu under A picks up a d mu lambda term under a gauge transformation. So that means that the Lagrangian picks up a d mu lambda times j mu term, which, up to a total derivative term that you can eliminate by integration by parts, is lambda times d mu j mu. Okay. So the statement of whether or not the theory is gauge invariant is the same as the statement of whether or not the current is conserved. Okay. But the point is that the current is now not conserved. And it's not conserved because of the additional coupling term here and because of the fact that it depends on phi. Okay. So you're going to need to add another term to this Lagrangian in order to make this current conserved again. Okay. So one way that we could proceed is that we could just start trying to guess terms that we could add to the Lagrangian, and eventually we would hit the right one. But instead, I would like to show you a neat trick. Okay. And in fact, the neat trick is anticipated by my notation, where I called the symmetry parameter here lambda, which is the same thing that I called the gauge parameter here. A priori, they don't necessarily have anything to do with one another. But in fact, the reason why I called them the same thing is that they are the same thing. So in particular, what we would like to do is the following. What we would like to do is imagine that when we do our gauge transformation, not only does A mu change, but phi should change as well. Now, unfortunately, I appear to have been using a minus sign in my notes. Okay, when I did this, so I'll just put a minus sign in there. It doesn't actually matter, but just to keep everything consistent. The idea being the following. Okay. Previously, when we talked about our complex scalar field, lambda, the symmetry parameter, was a constant. But I'm now imagining that it's going to be a function of x. And I'm going to identify it with the gauge parameter of electromagnetism. And the observation is the following. The observation is that if you consider the following combination of A and phi, called the covariant derivative of phi, then under a gauge transformation, this transforms in a very simple way. Under a gauge transformation, how does this transform? Well, it goes to d mu of e to the minus I lambda phi plus I times a mu plus d mu lambda times e to the minus I lambda phi. So let's just work that out. Well, from the first term, you'll get an e to the minus I lambda phi minus I times d mu lambda e to the minus I lambda phi. Okay. But that will cancel against this term here. So all you'll get is e to the minus I lambda phi plus I times d mu phi, sorry, plus I times a mu e to the minus I lambda phi, which is e to the minus I lambda times d mu phi. Okay. So what this means is that d mu phi times d mu phi bar is gauge invariant. So that if you want to write down the coupling of this charged scalar field to electromagnetism, all you need to do is take all of the derivatives of phi that appear in the action and replace them by these covariant derivatives, capital D mu. So to make the theory gauge invariant, everywhere you see a regular derivative of phi, you replace it with a covariant derivative. So in particular, the action that describes a charged scalar field interacting with electromagnetism is just the action of electromagnetism plus the action of the charged scalar field, except now every time we write a derivative of the field phi, we instead use this formula for the covariant derivative. And let's just expand this out explicitly just to see what this extra term looks like. So let's just take, so if you just expand out that covariant derivative term, what does it look like? Well, the first term will be d mu phi squared, just the usual term, with no coupling between phi and a. And then you'll have minus m squared phi squared. Okay. And then the first term will come where you have 1a here mixing with 1 d phi. So you'll have I a mu times phi d mu phi bar minus its complex conjugate. Okay. So this is precisely the term that we called a mu j mu up above. So that quantity in parentheses is just the current. Then there's the correction term, which is the term that we didn't have up above, which looks like a mu times phi squared. Good. Okay. Are there any questions on this? Yes.
After when we want to maintain Gibbs invariance, is after we correct the Lagrangian in order for the current to be conserved.
That's right. Well, okay. To preserve gauge invariance, really, I mean, there's really a couple different reasons why you want to do it. I think the most important would be is that you don't want any additional polarizations of the photon. You know, you really want to be able to couple electromagnetism to charged matter in such a way that you're only coupling the degrees of freedom of electromagnetism to charged matter and not some other new degrees of freedom. Okay? If you didn't couple it in this way, then you would be describing a theory with more degrees of freedom. And what we're seeing is that in order to not introduce new degrees of freedom, we have this additional mysterious interaction term between the A's and the Phi's. Okay. So this is a very important Lagrangian. Okay. This is a Lagrangian. This is a theory that we're going to spend a lot of time studying in this course. Okay. This is the theory known as scalar quantum electrodynamics. So you imagine that phi is the field that describes the electron. The phi particles are electrons. The phi bar particles, the complex conjugates, are positrons. They carry opposite charge. And this is the action that describes the interaction of electrons and positrons with electromagnetism. And it's completely determined, it's completely fixed by our symmetry principles. It's completely fixed by gauge invariance. And the only thing wrong with this action, this theory, is that electrons and positrons have spin. Okay? So here we're really working in the approximation where electrons and positrons don't have spin, where we neglect the spin of the electron and the positron. So one can still extract a huge amount of physics from this, even neglecting the spin of the electron and the positron. And moreover, there are other theories where this is not just an approximation, but it's actually the correct theory. Okay? So there are cases where scalar fields do interact with electromagnetism. Superconductivity is one such theory. So in the theory of superconductivity, in superconducting materials, electrons combine together in pairs to form what are known as Cooper pairs, BCS pairs. Two spin 1/2 particles can combine into a spin 0 particle. Their spins can cancel. And so that means that inside a superconductor, you have electromagnetism coupled to a charged scalar field. And indeed, the phenomenon of superconductivity precisely arises because of this third mysterious term that we've written down here. Okay. So just to make that statement a little bit more explicit, one of the things that we see is that effectively this phi squared term here looks a little bit like a mass for the photon. Okay. In particular, let's imagine that we had some additional dynamics. So let's imagine, say, that you had some additional dynamics so that your theory was not just electromagnetism coupled to a scalar field, but rather that scalar field had some complex potential. Then if that potential had a minimum where phi was not equals to 0, okay, then that means that at leading order, near the minimum of that potential, it would look like this electromagnetic field had a mass. Okay. This is known as the Higgs mechanism. And in that case, the phi particle is called the Higgs. This is also the theory of superconductivity, okay, where the phi particle is the phi field is the field that describes a Cooper pair. In the context of superconductivity, I think it's relatively easy to understand why it is that the relationship of this to what you already know about superconductivity. So in particular, if phi is not equal to 0, then you'll have some effective mass for the gauge field, which is the value of phi at the minimum of this potential. And so this means that when you study the theory in a phase where phi is non-zero, your photons have become massive. Okay? And so inside a superconductor, photons are massive, or the effective photons that describe electromagnetism in a superconductor are massive. So for example, one of the famous features of a superconductor is what's known as the Meissner effect. That's the fact that superconductors expel magnetic fields. That's related to the fact that, as you saw, massive fields are short-range forces. They decay exponentially. And so that any time you have an electromagnetic field that's incident on a superconductor, it'll only penetrate it'll fall off exponentially inside the superconductor with a wavelength that's set by the value of the scalar field. Similarly, when we talk about the theory of the weak nuclear force, the analog of the photons for the weak nuclear force are the W's and Z bosons. Okay? Those are the analog of the photons. They're just like the photon, but they have mass, which is why nuclear forces are only relevant on very small distance scales. And their mass is set by the value of the scalar field where the potential is minimized. In that case, the scalar field is the Higgs particle, which was just discovered last year. And the masses of these gauge fields are quite heavy. Okay, yes, question.
Who picks the background potential for phi?
Well, okay, that's a good question. I mean, that background potential has to be determined by some other sort of dynamics. In the case of a superconductor, this phi is not a fundamental field. It's some sort of composite field where you have two electrons. And so it's determined by some very complicated dynamics. It's determined, normally electrons have like charge, so they would repel from one another. Okay, so they wouldn't want to bind together to form pairs. So the only way they can form pairs is if there's some sort of effective attractive interaction, which in the case of the superconductor comes from all sorts of lattice effects. It comes from the fact that these electrons are not primarily interacting with each other, but they're surrounded by clouds of other effective particles, so that the electrons that pair together aren't fundamental electrons, but electrons surrounded by clouds of other things coming from the material. In the case of the Higgs, nobody really knows where the potential comes from. It's something that we observe. Okay, what can I say? Where does it come from? I mean, another way that you might think about this is the following. So this potential V depends on the various parameters of the theory. So for example, if you think about a superconductor, you think about electrons moving in some atomic lattice. And as you change the properties of that structure, the structure of the potential will change. So when people study superconductors, it's very common to study superconductors as a function of various doping parameters, where you imagine a material and then you vary the fractions of different kinds of impurities and other sorts of constituents of that material. And as you do, the effective potential changes and the superconducting properties change. Things like the temperature at which there's a superconducting phase transition, things like the effective penetration depth of the wave of photons, which would be this parameter phi squared, are all functions of the various parameters that govern your theory. Okay? In the case of a superconductor, the master theory from which all of this is derived is the theory of electrons moving on some lattice of atoms. But of course, that's a very hard theory to solve. So you just talk about it in terms of the low energy approximate theory, which is the theory of scalar QED that we've written down here, possibly with some potential. In the case of the Higgs mechanism in the Standard Model, this is the question of where do the parameters in the Standard Model come from? We don't really know the answer to that. I mean, there are various sort of symmetry principles that allow us to constrain lots of things. There are various principles that allow us to have order of magnitude estimates. In many cases, those estimates are off. So for example, if you just try and think very generally about what the Higgs mass should be in a theory of in a generic theory of quantum fields coupled to gravity and coupled to all this other stuff, you'll get an estimate for the effective mass of the W's and Z's that's off by 15 orders of magnitude. This is known as the hierarchy problem. It's one of the biggest problems in particle physics. So the answer, where do these parameters come from, is a good, so that's a difficult question to answer. Okay. Yes?
So if we are in a closed space or in another space, really do affect the kind of potential.
Absolutely. So let me give you another example. So let's imagine that you're studying the very early universe. Okay. So we saw in the case of the Higgs mechanism, we saw that whether these gauge fields, whether the gauge fields that mediate the nuclear force have a mass, depends on the form of this potential V. Okay. The form of the potential depends, if you put a theory at finite temperature, that will affect the form of this potential. Okay. And in the very early universe, the universe was very hot, so it was at very high temperature. And so the gauge fields associated with with the nuclear forces were effectively massless in the very early universe. When people talk about inflation, for example, they're talking about a theory, a phase of the universe that was at vastly higher temperatures than those associated with the Standard Model of particle physics. So the gauge fields of the Standard Model of particle physics were effectively massless. If you like, today we're in a superconducting state, and in the early universe we were not in a superconducting state. Today, the reason why the nuclear forces are short distance is that we're in a superconducting state. Not superconducting for the electromagnetic field, but superconducting for the analogous gauge fields associated with the nuclear forces. But in the very early universe, we were in a non-superconducting state. Okay. The history of the universe is one of phase transition. It's one of phase transitions, for example, from this non-superconducting state into the superconducting state at low temperatures. You might not think we're at low temperatures, but relative to sort of fundamental scales like the Planck scale, we're at very low temperatures. And so we're in essentially a superconducting phase. Okay. I think the importance of this theory really cannot be overstated. So we're going to spend, next class, what I'm going to do, we've constructed the theory classically. Next class, what we're going to do is construct it quantum mechanically. We're going to learn the Feynman diagrams that we use to study this theory. And then we'll spend maybe a week or so working, hopefully not too much longer, on scalar quantum electrodynamics before moving on to real full-fledged electrodynamics with spinors. Okay. All right, see you next week. And if you haven't picked up your problem set, go ahead and grab that now.